All right, in the last video, we learned how to use the periodic table to do electron configurations. We have the S block, P block, D block, F block. We need to deal with, in this video, the idea of ions, and we also need to deal with some weird exceptions. You will find that the D block is pretty much going to screw up any rule that we have. That's kind of a common trend. So ions. We've seen ions before, not a huge deal. Okay, if you have cations, the general rule of thumb, these are things with positive charges, you essentially just remove the last added electrons. Okay, so for example, if you have calcium, periodic table, calcium is element 20, so it'd be argon 4s2. Okay, this would be a neutral. Now calcium typically forms a +2 charge because it's in the second column, so great. We just remove these last two electrons that we added. So it's just argon, which is why things in the second column form a noble gas, or form a +2 charge, because they're left with a noble gas electron configuration. They tend to be very, very stable. Anions are literally the exact opposite idea. Okay, these are negative, and you literally just keep adding electrons. These ones are even easier. Okay, so for example, I don't know, let's, sulfur. Okay, if we look at the electron configurations, sulfur is neon, 3s2, 3p, 1, 2, 3, 4. Okay, great. Sulfur is in column 6A. It tends to form a -2 charge. So you just add electrons. So we add 2 electrons to this. So we get neon, 3s2, 3p6, which is the same thing as argon. I am perfectly comfortable with you visualizing, okay, it's got 2 more electrons, great, it's argon. The reason it forms a -2 charge in the first place is to be like a noble gas. If you can abbreviate it as noble gas, please, please do so. It's easier. So, how to deal with cations and anions? Doesn't seem too bad. Pretty straightforward, pretty good, okay? Except the D block. The D block screws everything up. So, let's see if I can phrase this correctly. So these are things in the D block are metals. Metals only form cations. So cations in the D block. This is gonna get a little complicated. So I want to make sure I am phrasing this correctly. So the idea is you're still removing the last electrons added. That part doesn't inherently change. This is the foundational rule. This is what everything else is built on. The problem is that it turns out, like if you have like 4s and then 3d, it turns out that the 4s electrons actually get removed first, even though the 3d were the last ones added. So if you have to choose between s and d electrons getting removed first, the s orbital electrons get removed first. So in other words, if your choice is between S and D, the S get ripped off first, even though they got added first. So here's what I'm thinking. Here's an example. Iron. Okay, if we look at this, iron is argon, 4s2, this is 3d, 3d, 1, 2, 3, 4, 5, 6. Iron can form two possible charges, 2 plus or 3 plus. If we have a 2 plus, our choice is between removing an S or a D. I know the ground rule says to remove the last ones added, but anytime there's a D block, it pretty much ignores the main rule. So the S electrons get removed first, so your answer is argon 3d6. Okay, these are the two that get removed first. If you have Fe3 plus, we've already removed the S electrons, now we just remove the last ones. We don't have that choice anymore, so there's no concern. So now it's argon 3d5. Right? A little weird. The D block messes things up, it's just how it works. Let's try one more example. Let's try 10. Okay. Sn is krypton, 5s2, 4d10, 5p12. Okay, 10 can form two possible charges, 2 plus or 4 plus. If it's 2 plus, the ground rule, the base rule that we decide everything off of is you remove the last electrons added. Our choice is not between S and D. We have p orbitals, so those are the first two to get removed. Okay, great. Not a big deal. Everything's taken care of. Now, to remove another 2 electrons, our choice is between S and D, so the S get removed first. That's what this rule means. Okay, so whether you start with something in the D block or not, because S is over in the P block, anytime there's D orbitals in here, things get a little messy. Okay, not too impossible, but definitely adds a little glitch to the otherwise super simple method. Okay. We need to talk about something called orbital stability. Kind of switching gears here to get to the next topic. Not an exciting topic, but it does help us decide things in the future. I would love to say that there's always like a nice straightforward answer, but this makes things complicated. Again, the D block screws it up. So if you have a full orbital, so for an S orbital, this would be 2 electrons. For a P, this would be 6. For a D orbital, this would be 10. Or an F orbital, this would be 14. That is the most stable option available. That is the best, most stable thing it can be. Okay. It turns out that the next best option is to have a half-filled orbital. Okay. So for like a D orbital, this would be 10 electrons, this would be 5. It turns out that having 5 is better than 1, 2, 3, 4, 6, 7, 8, and 9. Okay. And then the least stable is any other option, which I'm going to just call partially filled. I don't know what else to call it. Okay, so for example, if you had a D orbital, I'm actually going to draw the orbitals, the boxes, just so you can see it a little better. D orbitals have 5 boxes. A full orbital, everything goes up and then everything gets paired. This is the most stable option available. This is better, so this is a full. A half-filled is where essentially we only have the up arrows. 1, 2, 3, 4, 5. Remember, we don't start pairing them until we get past that. And a partially filled is literally any other option. If any of these have if any of these have 2 or have 0, if it's not full or half filled, you're pretty much messed up. So, any other option. Okay, not a hugely complicated thing. It does affect p orbitals and f orbitals and s orbitals also, but d orbitals are the main thing we usually pay attention to here. Okay, so the consequence is that even though we just learned how to do electron configurations really well in the last video using the periodic table, there are exceptions that we need to learn. And, as you may have guessed, the exceptions exist primarily in the D block. Okay, so if you look at the periodic table, the exceptions are column, I guess this would be, I'm just going to write on this particular periodic table just for right now. This is 1, 2, 3, or sorry, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, it turns out that column 11 and column 6 are the ones that are most responsible for all the weirdness. Okay, so column 11 is copper, silver, and gold. Shouldn't be too hard to remember. They're pretty common things. I mean, they're rare and expensive, but like that you've heard of them. Okay. So, for example, let's look at copper. The expected value, or the expected answer for the electron configuration would be argon 4s2 3d9, right? This is the expected answer. It turns out that the actual answer is this. Because having a full d orbital is the best option available, it actually steals one of the s orbitals, or s electrons, to make sure this is full. So I guess I could label this as actual. And the idea is this is a full d orbital. Okay. P orbitals won't do this. It's only d orbitals that make this weird little glitch. But this is actually the value for copper. So this one is actually not correct, even though that's what you would have totally expected it to be. Because this is more stable. The d orbital will steal an electron to stabilize the overall atom. Okay? Things in column 6 do the same thing also. Column 6 is chromium, probably should write my letters legible, sorry. Chromium, molybdenum, and tungsten. I'm sure that seaborgium might also do something, but it's radioactive and I honestly don't care. It's anything past element 92, I'm just going to ignore it. So, let's look at molybdenum. I'm actually going to draw, this works for orbital diagrams too. Anything that applies to electron configurations also applies to orbital diagrams. So I'm going to draw the orbital diagram of this so you can maybe see what's going on a little better. So molybdenum is krypton 5s2 4d 1 2 3 4. So krypton 5s2 1 2 3 4 is 4d4. This is the expected answer. Okay. And it's the same type of thing. It'll basically steal one of the s electrons because this is one away from being full. Or one away from being half full. So what actually happens here is this paired electron actually gets ripped up and moved over to here. So the actual answer is 5s1, 2, 3, 4, 4d, 1, 2, 3, 4, 5. So it's the same logic as up here. It steals one of the s electrons to make this more stable. But the reason this is doing this is half filled, which is better than partially filled. Okay, it's not as good as this, but it does it. This is how this works. Okay, so these are the two main columns on the periodic table that do this, column 6, column 11, and you'll note column 6 is 1 away from being half filled and column 11 is 1 away from being filled. There are no weird exceptions in the p block. This is pretty much exclusive to the d orbitals. And then there's one more exception. Palladium. One element all by itself. The rest of the column doesn't do this. Palladium is oddball enough, it's 2 away from being filled. It actually steals both of the s electrons. Okay, so this steals 2 s electrons. Okay, so palladium, we would expect it to be, element 46, expect it to be krypton 5s2 48. Just gonna do electron configurations here. 5s2 4d8. Okay, it will actually steal both of these and move it up here. And what you end up with is palladium is actually just krypton 4d10, which is a full orbital. There's not even an s orbital, so who cares? Everything's great. Okay, a little weird, not a huge deal. It does, but the problem is you're going to have to remember these exceptions, because anytime I ask for an electron configuration, this is the right answer and this is not, or this is the right answer and this is not. Okay, let's try a couple examples of both concepts and just kind of see how things go. Okay, so let's look at gallium 3+. Okay, so gallium is element 31. We would expect it to be argon 4s2 3d10 4p1. When we have a 3+ charge, we remove the 4p first, and now our choices are between the s and the d, so the s get removed first. So we remove 1p and 2 s's, so we just end up with argon 3d10. Okay, so the s electrons get removed first. Let's try let's go with silver. Let's do silver neutral, and then we'll do silver 1+. Okay, so silver neutral would be krypton 5s2 4d1 2 3 4 5 6 7 8 9. But in all honesty, this is one of the exception ones, so it'll actually be 5s1 4d10. Now, when we need to remove one electron, the other rule still applies, even though this has an exception. This is the other exception. So this one actually has both exceptions going on at the same time. So if you have a plus charge, this is what gets removed. The s gets removed before the d. Right? A little weird, not impossible though.